Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a theoretical physicist currently doing a postdoc at the Helsinki Institute of Physics over in the University of Helsinki in Finland. And I'm a cosmologist, so that means that I study the universe, the contents of the universe, how things evolve, how things interact, cool stuff happening inside the universe. It really is a great topic. I really enjoy being a cosmologist. I love getting to work on these random topics in the universe. And I love chatting to everybody about all of the cool things I get to work on and about science, about cosmology in general. So for anybody who doesn't yet know, this is an interactive stream. The idea here is that you people can ask me anything you want. You can ask me about cosmology, about space, about the universe, which are all kind of the same umbrella term. You can ask me about physics, about academia, about myself in general, basically anything you want. This is an Ask Me Anything. You can ask me whatever you want, and I will do my best to try to answer. If you're a first-time viewer, welcome. If you're a regular, welcome back. It's really, really great to have everybody here. Really nice to see some of the regulars coming in and to have new viewers as well. I do believe there was an issue with the way the YouTube video went up today and it did not send out notifications. I know because I'm subscribed to my own channel on a different account and I did not get a notification. So I also see that the numbers are still quite stagnant. So maybe people did not get the notification today, which is possible. And it's unfortunate that this has happened when I'm just coming back from a few weeks break because Cup of Cosmology has been on a break for a few weeks, but now it is indeed back. And I am currently not seeing any comments coming in. So if someone could, if you're watching, please leave a comment to check if the comments aren't working. There might be an issue on the restream side. But yes, Cup of Cosmology has been away for a couple of weeks. I have been traveling. I have been doing a bunch of stuff, which means there have not been any videos in a while. But today I am back and very happy to be back to chat to everybody about all of the cool things I get to work on. And I'm just going to do a slight test because I do believe there is an issue with YouTube. Okay, just doing a test. Hey, Alok, great to see you. Thank you for your comment. Nice to see you here. Thank you. I am very tired, but good. Okay, I'm starting to see the comments coming. I don't know what just happened there. There was an issue where I wasn't getting comments, but now it seems to be coming through. Excellent. Okay, so great to see some of the regulars coming in. Great to see some first-time viewers here as well. Alok, Prath, and Meetup. Great to see you all here. Welcome. Yes, Cup of Cosmology has been away. Hey, Paul, great to see you as well. I was hoping you'd be in today. Always nice to have you here. Yeah, Cup of Cosmology has been off for a couple of weeks because I was in Spain on holiday, helping with the house move and doing a not very relaxing holiday, but a very fun holiday. And last week I was just too tired to do a stream, which is why there was no stream last week. See, we also have Shorty and John. Great to see everybody here. I know some of you had been waiting for emails from me for quite a while. Today I actually cleared the Cup of Cosmology inbox. So if you sent me an email at some point in the last 5 months, 6 months even, you should have had an answer today. So I know some of you were waiting quite a while for those emails. I do apologize. I spend most of my week answering emails at the weekend. I'm like, meh. So Cup of Cosmology emails always take a while, but I do try to answer everyone who emails me, and I sent out a bunch of them today. So if you've been waiting for an email, hopefully you got it today. And again, for anyone who does email me or send me a message on whatever platform, thank you. I really, really do appreciate it. Some of you just send me messages just to say hi. I do appreciate that people reach out and ask questions. It is always nice to see the community that we have here. And even if I don't get back to you soon, I hope you all know that I do appreciate your emails. On that note, if you want to email me, the email address is contact@cupofcosmology.com, and you can reach out to me on the Cup of Cosmology Instagram profile. Also want to make a comment there, please don't try to reach out to me on my private Instagram profile. My personal account is private specifically because I want to keep it separate from Cup of Cosmology. So you're welcome to reach out to me on any of my Cup of Cosmology social media. If you try to reach out to me on my private one and I don't know you personally, I'm not going to reply. Just need to make that comment again based on some things recently. Nothing bad, don't worry. Okay, a comment from Prath. Wasn't expecting a stream today. Thought there was still one more weekend to go. It was supposed to be actually last weekend. I initially said I'd be away for at least 2 weeks, maybe 3. I was away for 3 in the end, so that meant back today. Not sure if I should be back today, given that I currently have a neck injury, but who cares about that? I wanted to come on and chat universe to everybody. So there is no topic planned today. This is an interactive stream. This means that you people get to ask me whatever you want, and I will do my best to try to answer. I don't have all the answers, but I will do my best to answer whatever I can. But this means that you people need to ask questions. If you ask questions, I can answer. If you don't ask questions, I get to talk about some of my favorite things in the universe. For an example, what the universe is made of, or how we measure the universe, all of these things. As always, there are some prompt questions you can see in the YouTube description. If you're lacking questions, you can always ask me those questions. So let's start with, what is the universe made of? I'm just going to start rambling. Jump in with your questions at any point. The universe is made up of three main components: everything we see, everything we're used to, everything from me to my tea mug, to the night sky, or the stars we see in the night sky. All of this is normal matter. Normal matter only accounts for 5% of the energy budget of the observable universe. There's another 26% that is in the form of dark matter. Dark matter is this weird type of matter that interacts gravitationally but doesn't interact electromagnetically. This means that we can't see dark matter. As far as light is concerned, dark matter is not there, which makes it very difficult to study. The remaining almost 70% is in the form of dark energy. Dark energy is this weird type of energy that is driving the accelerated expansion of the universe, and that is pretty much everything we know about dark energy, which is fun because I've just said I'm a cosmologist, I study the universe, but there's 95% of the universe we don't know much about. How do we know these numbers? Where do these numbers come from? These numbers come from the cosmic microwave background radiation. This is a snapshot of what the universe looked like 380,000 years after the end of inflation. It is basically a picture of the baby universe. This is what we get when we look anywhere in the universe. At the background behind everything else, there is this afterglow of the Big Bang, this background light, which is in the microwave range of the electromagnetic spectrum. It is everywhere. This is why we call it cosmic microwave background radiation. The different temperature, the different colors that you can see here, the orange and the blue, correspond to slightly hotter and colder regions in this early universe soup. And by taking the statistical properties of these orange blobs and blue blobs, we can figure out what the universe looked like and what it looks like today. And from the CMB is where we get these very precise numbers here of the universe being made of 4.9% normal matter and so on. And for anybody keeping track, it did indeed take less than 10 minutes to get the CMB today. We did indeed get it quite early this time. Comment from Prath about neck injury and the keffiyeh. Yeah, so I do like wearing the keffiyeh. It's fashionable, it's cool. It's good to stand up in solidarity. This bit has a lot of meaning behind it. I like wearing it. I don't usually wear it indoors. I have a pinched nerve in my neck, which is pretty painful. I'm quite heavily medicated today. But I was told to keep chills off your neck, try wearing a scarf the entire time. So I've been told to wear a scarf inside the house. And if I'm going to wear something around my neck inside the house, I'm going to make a political statement about it at the same time. But yes, it is also extremely cozy. I have to say, this is like super comfy to wear. Okay, I see we have a few comments coming in already. See, the problem with taking a break in streams is that then my voice is like, wait, what are we doing again? How does this work? What is talking for an hour? Even though, like, since getting back from my holiday, I've already given 2 talks, and both of those for 1 hour. So minor detail here. Okay, I see a few questions. Thank you for the questions. I was just warming up here with CMB just to give you time to think. And now I see we have 3-4 questions to jump into. There's one from Paul here. Could you talk about teams in your work? Do you have a core group who works together like a traditional office? Or is it more loose, interacting with far-flung people different times? That is a really nice question. And I would say it's a mix of all of the above. So it also very much depends on the institute where you are and the group that you're in. In my current university, I'm part of what is known as the computational field theory group. The computational field theory group is a group of 3 professors, 2 postdocs, and a bunch of master students, and PhD students, of course. And we all work on very closely related topics. The main theme in this group is phase transitions in the early universe, or funky stuff in the early universe that could produce gravitational waves. We all approach this from different sides, and I collaborate with different people within the computational field theory group. Some of my projects are more with some people, some are more with the others. There's some people who I have no interaction with. Then I also have The computational field theory group is embedded in the wider cosmology group. The cosmology group is about 40 people. There we have people working on very different topics. You have some neutron star people, we have some inflation people, some who you've seen on the streams before, some people working on holography. Then this is part of some people in the cosmology group and the computational field theory group are also part of the Helsinki Institute of Physics, which is broader and includes research groups in different universities. And then, of course, we are embedded in the University of Helsinki. However, I have collaborators spread across the world. I have collaborators in many different countries. What often happens, because we move around a lot to change postdocs, to change jobs in between your PhD, we often change research groups. But the projects that we start are not contained to us being in that place. Like the projects that I started during my PhD did not finish when I finished my PhD, not all of them. So then as collaborators spread out, you start collaborating with people in different research groups. I currently have a project ongoing that involves collaborators I think the project involves collaborators in 5 countries. At some point, we were all in the same place, most of us. And then we spread out and then we loop in other people like, oh, I have a student who has this expertise, let me loop them in. So then we end up getting quite a diverse group. Now, in terms of my local group, that's in terms of collaboration. So I have projects that are spread out across the world, and I have projects that are more focused on the local groups. Especially as a postdoc, whether I'm supervising students, I'm going to be working more with the people that I'm supervising, the PhD students that I'm supervising, the master students, the bachelor students. But then, as I said, I'm part of the computational field theory group, but I don't necessarily collaborate with everybody in this group. We try to have I've kind of set up something where once a month everyone in the computational field theory group comes together and we just update each other on what we're doing. Because sometimes it can happen that someone's working 2 offices down from me in my same group and I have no idea what they're working on because we don't talk to each other enough. So we do try to have a monthly meeting where we all gather and chat. And then we also have cosmology seminars, we have broader things. And we do something to kind of build up team spirit, which I like a lot, which we're actually doing in 2 weeks, which is our yearly retreat where everybody in the computational field theory group goes away, usually to a very like horror film style scenery. We go to a cabin or a venue in the middle of the forest for 3 days and we work. There's a lot of work, but there's also a lot of like, movie night, let's bake something. We have a makeshift kitchen. And it's really fun because it's a good chance for us all to figure out what everyone is doing, where we overlap, and new projects often come up at these retreats. And it's also a chance for the students to kind of corner the seniors and ask for advice, ask questions, and kind of really interact. So I know that was a long-winded question there, but going back, Paul's question was, could I talk about teams? Do I have a core group? Is it far-flung? So I have collaborators across the world. The people I work most with right now is, of course, the person who hired me because they hired me for a reason. We have very similar interests. We work together on a few projects. I also work a lot with a PhD student. We put out a paper very recently, the PhD student and I'm supervising. But then there's other people in the computational field theory group who we're just a bit too far away in research topics. So there's not a clear collaboration, but we still do try to interact and make sure we know what everybody is doing. So the group structure very much depends on the place. Like when I was in Brussels, I worked with 2 of the group members and literally nobody else. So it very much, I should stop moving. So it very much depends where you are, the research group you are, but it's usually a mix of local collaborators and international collaborators. Hope that answers your question, Paul. I'm always happy to talk about this as well. I think it's very good to understand about different group structures and dynamics and how things work at different places. I like the way our group is set up here. I feel like we have a good mix of how we collaborate with different people. So I think it's done in a nice way. Going away to a horror film type cosmology venue, yes, spooky action at a distance. That's what we should call our retreats. I never really think about them as being horror film-esque until I tell other people. It's like, yeah, we're taking a bus to the middle of nowhere. There's not much phone signal. We'll be there for 3 days. It's in a cabin. It's good. It's good. So we don't. I don't think of it as being horror film. There's always sauna. There's always a lake. And then I mention it to people, and they're like, "So you're going into a cabin in the woods next to a lake in the middle of nowhere? communicated with people for 4 days. And I'm like, oh, well, when you phrase it like that. But we haven't had any, the creepiest thing that's happened is we watched a slightly dark film series last year. It's all good. It's all good. Yes, I will post videos or photos at some point of the retreat. Oh, maybe I could do an outreach event at the retreat. Oh, no one can run away in the cabin in the woods. Nice. Okay, pin that. Come back to that. Going back to the questions, I'm going to skip one and then go back to it in a minute. There was a question from Shawnee. How much mathematics do you need to become a cosmologist? I read two questions and then mixed them. So how much math do you need to become a cosmologist? Depends what branch of cosmology. I think there's some things that are essential to most physicists. Math is the language we use to describe phenomena in the universe. So things like differential calculus, how to solve integrals, this is stuff that we need to know how to do, but also not really in depth. Like when I studied calculus and integration in my bachelor's, we would do a lot of these random integrations, and there's tables for that, there's computers for that. But kind of the general principles behind it, how to play about with numbers, how to get them to do what you want them to do, is something we do need a lot. So I think definitely algebra, calculus, differential equations, these are things that are essential going into any branch of physics. Now, a lot of what I do is computational cosmology, so I tell the computer to do physics for me, mainly because then I don't have to do the derivations or the calculations myself. But I still need to know the equations to put into the computer, so I still do need some element of math. Then within cosmology, you get people who are very, very math heavy. Like there are people who we call the pen and paper people, whose mission is to derive an equation more precisely than it has been before. And this is a 5-page calculation at least. And it's an incredible result that advances our knowledge about that, how that property works or how we can describe something. But that's not the type of cosmology I like doing. I'm much more of a computer type cosmologist. But the pen and paper ones, as we call them, are incredibly important for giving us the equations. So I would say you do need a fair amount of math to go into cosmology, but not as much as in other fields. Like if you're doing hardcore theoretical physics, you probably need more. I'm slightly more on the observational side. As Paul is just mentioning here, statistics is important. So there's statistics that are done at different levels, like some general idea of statistics I think we all need, but then getting really in depth into statistics. Like I do a lot of Bayesian analysis and Monte Carlo chains, so I need to know perhaps more statistics than the people who derive the theories for us. So it very much depends which type of cosmology you're doing, how much math you're going to encounter on a day-to-day basis. I think a lot of what I do is more on the statistics side. Now, if someone gives me an equation, it's like, can you derive this? I probably can sit down and do it. I don't like doing it. I'd much rather play about with codes. But then when I analyze data and get something out of it, I need to know how to interpret it. And often that's playing about with numbers. So yes, there is math. Less than some of my colleagues, more than some of my other colleagues, different types of math. Following on with this, I know there are questions that I will get to. Following on with this is a comment from Prath. How much programming do you need to know and which languages? So there are people in the computational field theory group who do not do any programming. And there are people who do a lot of programming. Again, there's very much different types of cosmology you can do even within the same group. There are people who are trying to figure out how to more accurately describe how these phase transitions in the early universe happen. There are people doing that. And for that, they don't really need the programming side. But then when I take their results and put them on the computer, I need more programming. So you can be a cosmologist without doing any programming. But I feel like gradually more and more, a lot of what we do, especially me personally, is more computer-based, more programming-based. So a lot of what I do is getting the computer to do physics for me. So I need to know programming. It is not a requirement to be a cosmologist, however. I think there's a lot of cosmologists who don't know how to program. And this goes back to the type of team that you work on. Often on a paper you get, or on an article or a project, You get people with different expertise, and maybe this person does more of the coding side, and this person does more of the analytical calculations, and this person does more of the data side. And on different projects, I've been the expert on different topics. I had a paper where I was a cosmologist working with particle physicists. I've had a paper where my main role is being the statistician. I've had projects where my main role is being the data analyst. So it very much depends on the project. As to which languages, most of what I do is either in Python or in C++. Python is just much more intuitive and nicer to use, but you do need C or C++ for the quick background. Like a lot of the libraries that Python calls are written in C and C++. So I have codes written in both. I know there's also a push by some people lately to switch to Julia. Apparently Julia is very powerful. I have not got there yet. The first code I ever touched in a physics context was in Fortran. I took one look at it and said, nope, and rewrote it in C++ because I didn't want to touch Fortran. So most of what I do is either in Python, C, or C++, but it, again, will depend on who you talk to. There's also some people who do a lot of amazing cosmology and they do everything in Mathematica. I'm like, why would you do that to yourself? But good for them. You know, I have worked with Mathematica. I don't particularly enjoy working with Mathematica. So the languages that I need or that I use are Python, C, and C++. But you can do cosmology without knowing how to program. It is not a requirement. I feel like some general math is necessary to become a cosmologist, but I wouldn't say that programming is a requirement. Very much depends on what you do. If you want to make pretty visualizations of data, you probably need some programming background as well. Okay, now let's jump into more physics questions. Although I saw there was some comments here. Oh, it's laggy today. When I scroll in the comments, it's laggy. That is going to annoy me very quickly. Okay, I saw there were some more questions that I want to get to. A comment from Shawnee here first. Whenever I say to people I want to be a cosmologist, they think I say cosmetologist. It happens. It happens a lot. And this is why when I actually started Cup of Cosmology, back before it was called Cup of Cosmology, rather than having, so now the title is like Cup of Cosmology, let's talk about the universe. The first few that I did actually had the title of I'm an astrophysicist, let's talk about the universe. Because in the early days of my streams, when I was on Periscope, if I put I'm a cosmologist, let's talk about the universe, I'd get people come in and ask me cosmetology advice, which is probably a terrible idea given my complete lack of knowledge in terms of cosmetology. You know, I don't use products, I don't know anything about them. I can probably identify eyeliner in a lineup, maybe, from my goth days. But yeah, so it happens. And for a long time, I would use the term astrophysicist instead of cosmologist. But I feel like that just leans into the problem. People are not being malicious. It's the same as when people mix up astrology and astronomy. It doesn't come from a place of malice. It comes from a place where people haven't been exposed to what cosmology and astronomy is. And by me using the term astrophysics, I'm kind of making the term cosmology even more obscure. So I understand that it's very frustrating that you say you want to be a cosmologist and people think you're saying cosmetologist, but it's also a chance to introduce them to the joys of the universe, right? It's their lucky day. You get to tell them like, no, I get to study this cool thing in the universe. I get to work on CMB and dark matter. It's a chance. It's a learning opportunity. So even though it can be very frustrating when people ask me if I study astrology or cosmetology, it is a learning opportunity. It is a chance to tell people about the cool things I actually work on. And I think that's very cool. So for a while, I didn't use the phrase cosmologist because I knew what people would think. But then I would make jokes like, come for the cosmetology, stay for the CMB. You know, you can just lean into it, embrace it. Comment here from Paul. I think it might be a little worse than astrology versus astronomy because there might be a gender bias assuming cosmetologists. There absolutely is. That is something that does happen. I was just getting rid of what I believe is a bot here in the comments, or someone who is very weird in their approach, but I guess a bot just just block that. Yeah, there is absolutely a gender bias where if I say I'm a cosmologist, people are like, oh, did you mean cosmetologist? Because there is a perception that cosmology is for men, science is for men. This is unfortunately a bias that people still have. The day I went to open doors at my university when I was 18, I went up to the physics stand and the guy just took one look at me and said, biology's over that way. I am still annoyed at this. It has been 15 years. Oh my God. It has been 15 years and I am still annoyed at this. So, yes, there is a gender bias. But this is something that also I believe we need more exposure. You know, the more people who look like the non-traditional scientists, the more diverse people we have saying, hey, I study these amazing things, the more we're doing to break the stereotype that this is a man's world. It is, unfortunately, but we're going to change that. The sea is now perfect temperature. So, yeah, there is indeed a gender bias where people assume cosmetologist when they see me instead of assuming cosmology. There could be a gender bias at play, and it could also be, again, trying not to issue malice on people, could also be that people have just never heard the word cosmology before, and that's okay. Comment from Prathu, I had a goth phase. Yes, it wasn't just a phase, it was like a 5-year long thing where I dressed very goth. I still on occasion do. I still have a lot of my outfits. And on occasion I'm like, today's a kind of goth day. In my goth years, it was very common to see me with eyeliner and smoky eyeshadow. So I didn't actually like, because I don't like wearing makeup personally, but yes, I don't like wearing makeup personally, but I did for the aesthetic. I was in my full-on goth phase while living in Spain, and I would still wear my leather boots and floor-length leather jacket in summer because it looked good. So yes, I went through a pretty big goth phase. Some people have joked in the past that I should someday do a cup of cosmology in goth get up. It's nearly Halloween. Maybe I do a cup of cosmology in Halloween costume this year. That would be fun. Okay, so getting back to the actual physics questions, all of these questions have been very interesting. I saw there were some physics ones. Let's see, going back to the top. There was a comment from Arlo. Could you talk a little about initial mass function? Is it something related to galaxies? See, initial mass function rings a bell, but I can't remember off the top of my head what it is. Just based on the name, I would imagine it's the function or the mathematical description you use to describe the initial mass of a system. For an example, if you have a bunch of galaxies, these galaxies are going to move, but you want to know how they start off before things start happening. You might use something called an initial mass function. However, I know that initial mass function applies to a specific concept, which I currently can't remember. So let me do the usual thing we do. If in doubt, ask the internet. Initial mass function, just to see if it triggers my memory of what it is. It is indeed something that is astronomy related, yes. Okay, so the initial mass function describes the initial distribution of masses for a population of stars. Okay, yes. So as you can see, I just Googled it, figured out what it was going to trigger in my brain. This is what we do when we don't know the answer to things. Not an expert on this, very much not an expert on this. But when you have stars forming in a galaxy, these stars are going to move around a lot. You're going to have a lot of stuff in between the stars, a lot of hydrogen, a lot of helium, and you're going to have stars that are going to start interacting with each other. So the way this system evolves is going to be something that is not quite easy to describe. So when you want to talk about the system, you need to know how things started off. And for this, you start with what is known as the initial mass function, which describes the starting point of the stellar evolution phase inside galaxies. That is literally everything I can say about stellar mass function, because I just asked Google to see if it triggered something. Goth days, you heard goth phase. Yeah, it was a phase that lasted like 5 years. A cup of cosmology. Okay, I love a cup of cosmology. That has to happen now. It would not be too difficult. There's a costume party in 2 weeks that I really want to go to that has the theme Harvest Witches. It's like take witches but make them autumn themed. I have so many ideas for this costume party. The problem is, it is literally like an hour after I get off of the bus coming back from the group retreat. So it would either I take my outfit with me and go directly from the group retreat to the costume party, where I basically have 1 hour to get changed and get myself downtown for costume party. But Harvest Witches, I have to go to that. Okay. I should try to minimize how much I'm moving my head, and I am very much not doing that right now. Back to the questions. Where were we? We talked about mass function. Right, there was a question from John here. Long question. I like the long question. Question from John. Do gravitational waves diffract around massive objects? Could some future detector maybe do gravitational wave double slit experiments as they diffract around the sun or planets? Excellent question. The answer is yes. So gravitational waves are ripples in the fabric of space-time caused by anything massive moving through the universe or anything that moves in a non-symmetrical way. So I'm going to do the usual example, and this is a terrible idea. If I start waving my arms around randomly, this is going to produce gravitational waves because it's not a symmetric motion. However, if I'm just rotating on my chair, keeping my head straight, if I'm just rotating on my chair, I am not producing gravitational waves because it's a symmetrical movement. You see the movement here is completely symmetrical. But any object that does not have symmetry and is moving through the universe, for an example, 2 planets rotating around each other, 2 black holes rotating around each other, this is going to produce gravitational waves. Gravitational waves are these ripples in space-time that propagate throughout the universe. They're very, very, very cool. We can use gravitational waves to study everything from black holes to the very, very early universe. Gravitational waves, ripples in space-time. So we know that space-time permeates all of the universe. Everything in the universe is embedded within space-time. So if you have ripples in space-time where you change the distance and the time of something very slightly, this is something that is going to interact with anything that has gravity. We pull it back here. Gravity is the curvature of space-time. This is what we know from Einstein's general relativity. Objects with mass tell space-time how to bend. The bending of space-time tells objects how to move. Therefore, if you have any bending or distortion of space-time, it can be related to a gravitational object. When we talk about gravitational waves, they're ripples of gravity. They're waves of gravity, as the name implies. When a gravitational wave hits a massive object, it is going to notice the massive object. So you are going to get some fun effects. For an example, diffraction. Diffraction is where if you have a wave going through something, you can see diffraction if you're in the swimming pool and someone sends waves your way, you're going to break up the waves. The wave pattern behind you is going to be different than the wave when it comes towards you because you are an object that is diverting these waves around you. If you have a gravitational object in the universe, you can do the same with gravitational waves. So this means massive object in the universe, like a star or a planet, will disrupt an incoming gravitational wave. However, gravitational waves are tiny, 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 tiny effects. We are talking about something that is ridiculously small. If 2 black holes smash together somewhere in the universe and produce gravitational waves, by the time the gravitational waves reach me, the effect would be to make me grow. So if a gravitational wave comes through me, first I would get taller and thinner and then shorter and fatter. You have this kind of effect. But it would make me grow by 1/1000th the width of a human hair, which is ridiculously small. And yet we can measure this using lasers, which is still mind-blowing to me. So the point here is that gravitational waves are a tiny, 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 tiny effect. And we're talking about massive stars or massive black holes smashing together. They release a huge amount of energy, but the overall impact of the gravitational wave is tiny. So now if this gravitational wave hits a planet or a star, which are much, much, much smaller than the black holes that produce the gravitational wave, We're talking about a tiny, tiny, tiny effect on top of a tiny, tiny, tiny gravitational wave. So while diffraction and lensing and these type of things is something that is theoretically possible on top of gravitational waves, it's something that would be extremely difficult to measure because we need to have incredible sensitivity to be able to find the background gravitational waves and then distortions on top of this background of gravitational waves. This is something that is going to be very difficult to do. Now, we have a better chance if you have two supermassive black holes that smash together, and then there are other supermassive black holes in the way. That is something that is at least equal mass-ish of the initial quarrels, so it could have a slight effect. But it's still going to be a very, very small effect. So going back to the question that John asked somewhere here, could some future so do gravitational waves diffract around massive objects? Yes. Could some future detector maybe do gravitational wave double slit experiments as they diffract around the sun or planets? It's going to be very, very difficult. It's something that theoretically is possible, and I very much hope that several years in the future we will be able to do this. But we're not quite there yet. Right now we don't have the technology to do that, but people are looking for it. Once we have enough gravitational wave events, then you can start doing kind of population control of like, this is the standard, this one has an extra blip, this extra blip might be diffraction, might be lensing, might be something else. So first of all, we need to have enough population where enough stats, enough data on gravitational waves, and then we can say what is different to the normal. So what a diffraction pattern, for example, would look like, or what a lensing pattern would look like. So, conclusion, gravitational waves are really, really cool. Gravitational waves are ridiculously tiny. We can measure them using lasers. Amazing. Anything that has gravity or anything that has mass in the universe produces a gravitational effect. This means that any gravitational wave will be affected by any object with mass. However, these effects are ridiculously small. So it's something that is very, very far away in terms of being a possible tool that we can use. But maybe someday. See, there's a couple questions now of doing a double slit experiment using gravitational waves. So the idea of a double slit experiment, just in case anyone's not familiar with it, I'm just going to draw a sketch here. This is going to look like Wi-Fi. Okay, there. So when we talk about the double slit experiment, what we're talking about is you have a barrier here with two gaps. You see one gap here, one gap here. I shouldn't have used paper with lines, but there is one slit here, there is one slit here. A wave comes in this direction. When it goes through these slits, you're going to get a different interference pattern depending on the properties, because quantum physics is weird. But basically, when you go through the slits, and I've got random questions here, when you go through the slits, you're going to get a wave going here, a wave going here, and then this is going to interact with each other. Then you can do some fun things in quantum physics where if you're observing this, it behaves as a particle and it goes through one way. If you're not observing, it goes through both. Cool stuff like that. And then you look at the interference pattern. So if you wanted to do that with gravitational waves, you kind of need to do something in the opposite direction, right? Instead of a wall with slits, what is going to cause the disruption, I guess, would be the massive object. Just thinking out loud here. So let's do it in a different way. Let's say we have gravitational waves traveling through the universe going in the opposite direction now. Now I'm going to imagine I have two massive black holes here. I'm going to just drawing a sketch just to actually help myself think about what is happening here. So what I would imagine is you end up with something like this up here, where these are the two black holes. You have a gravitational wave and it would experience some effects around this. Then you might get an interference pattern here in the middle. Could you then use that interference pattern to try to learn about these two things? Maybe. I'm not completely sure. It's something that theoretically makes a lot of sense, but I'm not sure physically how we go about doing it. And at the end of the day, this thing that we're going to have here is also going to be a gravitational wave. It might look a bit different, but in order to know this, in order for the part in here to be meaningful, we'd also need to know what the parts on either side look like. So going about doing a double slit experiment with black holes, the way I would set it up, I guess, is using the black holes instead of slits, so a double black hole experiment. It is something that conceptually is going to be very difficult, also because if you have two black holes, they're producing their own gravitational waves. So then you have confounding effects. So I'm not sure if we can actually go about doing a double slit experiment with gravitational waves, but it's something very interesting to think about. I think what would actually happen is you just end up with such a big interference or an interference pattern that wouldn't really allow you to gain any further insight. And especially if we think a double slit experiment is set up to measure the particle wave nature of particles and waves. So doing that in with gravitational waves would not really give us much insight, but we could potentially, once we've reached a stage where we have really good grasp of all of the types of gravitational wave signals we can get, if something deviates from the norm, then we can try to figure out if or what caused that, what was in the path of this gravitational wave. But I don't really see huge advantages right now of doing a double slit experiment with black holes. But if we were to do one, this is kind of how I would imagine it, with two black holes and a gravitational wave. It's no longer a slit experiment, then it's a double black hole experiment, but it's very cool to think about. Comment from John here, you're going to think of double slit experiment when you see a Wi-Fi symbol. I mean, it's not a coincidence, right? A Wi-Fi symbol is actually supposed to be a wave. It's the waves of the internet. So it's not a coincidence that a Wi-Fi symbol looks like a series of waves. That is intentional. But it also means anytime I draw pictures like this of waves, I'm like, hey, look, my Wi-Fi is at five bars. I have good Wi-Fi. That is cool. But it's not a coincidence. Like the Wi-Fi symbol does have that origin. So physicist discovers that Wi-Fi symbol representing waves looks like waves. Yeah, it does. It's supposed to, but it does amuse me. Okay, more comments about the. I see Space Minus here saying that there's no useful purpose to a double slit experiment with gravitational waves. Well, yes and no. Like, I think the only purpose would be to study the stuff in between, so to study the black holes themselves. So it would be very different to a slit experiment, where you know the properties of the slit, but rather like using an interference pattern to try to study the gravitational waves, or to try to study the two black holes in between. Yeah, someone would do it because they can. I think it's the thing that doing this in space is something that is just unfeasible based on, like, you can't really get your black holes to behave the way you want them to do. And any type of gravitational wave we could produce in the lab would be too small to measure these effects. So I think more than setting up a double slit experiment using black holes, we might get lucky and find that configuration and then try to use that to understand stuff that happens. But it's not something we can really set up ourselves. It's not something that we can go about yet. You know, maybe a couple 100 years from now, we'll just play about with black holes like people playing about with marbles. Who knows? I don't see that happening, but it might. It would be cool. It's very hard to predict where we'll be 200 years from now. I don't yet think that 200 years from now we'll be moving black holes about. It would be fun if we had that technology. Okay. Good. Just go to the Pink Floyd laser show and get better results. Yeah. I mean, you get very cool results about how lasers behave. Not sure how much gravitational waves you'd pick up, but yeah. I feel like, as John is just saying, this whole thing of using black holes as a double slit experiment definitely falls much more into the realm of sci-fi, at least for now. But maybe in the future we can think about this. Okay, I think let's go back to questions. This was a question from quite a while, almost 40 minutes ago. Just took me a while to get there, about gravitational waves and diffraction. And then we talked about cosmology versus cosmetology, astronomy versus astrology. And then there was another question from John. Just a comment here from John that you're the opposite. When someone tells you they're a cosmetologist, you talk to them about galaxies and the CMB. I mean, fair. I do that regularly. Like, whatever someone works on, it's like, do you want to hear about the CMB? Do you want to hear about dark matter? What can I tell you about? Now, I gave a talk last Friday that was very much about gravitational waves and very much about phase transitions and early universe. And yet somehow I managed to sneak a CMB on one slide. And at some point in the talk, I was like, here's the CMB, my favorite thing in the universe, except right now it should be gravitational waves because I'm giving the talk on gravitational waves. So yes, it is always a good reason. You don't need an excuse to tell people about galaxies and the CMB. Why wouldn't people want to learn about it? It's amazing. And I realized I didn't say hi to David Dunn when David came in. Great to see you here, David. If you're still here, great to see you here. So there was a question from Shawnee some time ago. Is there a good university or community college that has a good branch of study in cosmology? Yes, lots all over the world. You'd have to narrow it down, like what country, where. I think often what is going to be the case is that during a bachelor's program or during an undergrad program, you won't see much cosmology, maybe one or two lectures at most. And where you really get into things like cosmology is at the master's level, the postgraduate level. So I think if you want to find a good college or university in terms of cosmology, what I would propose is look at which professors teach there or work there. If there's professors who are well known for being good cosmology educators or good cosmologists, then the university probably has a good cosmology program. A certain program at the university is only as good as the lecturers who impart that knowledge. So I think if you want to find a university or college that has a good cosmology program, I would look more at the postgraduate level and look at which professors are teaching those courses and do a background search on those professors. Also, it's okay to go into a degree without knowing what you want to work on. But if you do know what you want to work on, that's also something to bear in mind. Like if all the professors at a university work on string theory, for an example, in the cosmology group, and you're interested in dark matter, it's quite likely that the lecturers will teach the lecture from a perspective of a string theorist, and it might not cover up on topics that you find interesting. So if you already have an idea about which branch of cosmology you want to go into, finding lecturers who align with that is also very good. So I did my bachelor's in a university in Barcelona, one of the two in Barcelona. There are several in Catalonia. And I chose it based on the reputation of the university itself and also just what I liked about the courses being offered. For my master's degree, I chose a university based on the courses being offered. When I started my master's, I was a bit disappointed that there wasn't a good cosmologist teaching there at the time, but all of the courses really aligned with what I wanted. And just after I moved to Aachen, so did a very well-known cosmologist. And like the day he arrived, I was in his office saying, hey, I want to do a master's degree with you. Worked out. I did my master's and PhD with him. So yes, as to which universities have a good program for cosmology, it very much depends where you are. But if you want to discuss that more in detail, get in touch. I'm happy to discuss it if you get in touch. Okay. More questions. There was another one that I wanted to get to before. Where were we? I got distracted. We're going back. Answered that question. There was another question. There we go. That's the question I was looking for. Okay. I missed that one. I skipped a question. Where was it? Yes, there was a question from John. Another question from John early on. Is the rubber sheet analogy of space-time like a space-time diagram where the perpendicular direction is time? Is curvature then a representation of slowed down time towards a center of mass? Excellent questions. So the rubber sheet analogy is an analogy that is removed from mathematics. It's an analogy we use to try to explain how. Let me just check one thing there. Yeah, it's an analogy that we use to try to explain how gravity works, but it's an analogy that very quickly breaks down. So the idea here is you have a rubber sheet that's held up at all corners, and you roll a ball on it, and the sheet bends as the ball rolls past. What this is supposed to evoke is the imagery of space-time that bends as objects with mass go through it. It's a very nice visual parallel where you think of the sheet bending because there's an object with mass on it, and then you're like, yes, that is exactly what space-time does. The thing where it breaks down very quickly is that if you have this rubber sheet and you put an object on it, the reason that it distorts is because of the gravitational pull of the Earth underneath. So you're basically using gravity to explain gravity. So it's like, yeah, the sheet bends. Why does the sheet bend? Because there's a ball being pulled down by the curvature of the Earth. And then you start thinking, okay, so in space-time, what is pulling space-time down? And there the analogy breaks down. So the rubber sheet analogy is very, very good just as a visual comparison, just to have the idea. The way the sheet bends, let's just imagine there's nothing except the sheet and the object on it. The way the sheet bends with the gravitational object, like the planet. I just realized I'm covered in ink. I have no idea how I got covered in ink, probably with my pen. That would be a logical explanation. But yes, this rubber sheet is a very good analogy for the curvature of space-time at face value. But as soon as you poke at the mechanics of it, it breaks down. So I don't think you should try to draw parallels to how the equations of gravity actually work and how you fit curvature in this. It really is something that is useful for a visual comparison, but that is where the analogy has to end, because otherwise it becomes very difficult to explain gravity using gravity. It's like if a dictionary defines a word using that own word, it becomes cyclical. And this is the problem, that this rubber sheet analogy is very much just an analogy. So I wouldn't try to think too deeply about what it represents, because then you're going to run into contradictions very, very quickly. So just rechecking the phrasing of the question. Where was the question? Somewhere here. So the question was, is it like a space-time diagram where the perpendicular direction is time? Not really. It is just a visual representation of, look, fabric bends with massive object. Is curvature then a representation of slow time towards the center of mass? See, with the rubber sheet analogy, time is not playing a role. And this is very quickly where our analogy breaks down. So the rubber sheet analogy is great for a visual image. If you want to have a visual image of how space-time works, the rubber sheet analogy is a good one. To some degree, because the rubber sheet is two-dimensional, space-time is four-dimensional. So it is very much just something that helps us explain things, but I would say don't try to unpack it too much or pick it apart too much, because it very, very quickly breaks down. Okay, I think I answered all of the questions that were up there. Then we got on a tangent about a cup of cosmology. I love that piece, cup of cosmology. Okay, you see there's lots of talks here about bubbles and wave theory that I don't completely agree with, but I'm going to skip those because I feel like that was discussions amongst yourself. Okay, so where was I? Just saw comment from Shawnee. If infinity goes on forever, is it possible to fill it? Yes, with an infinite amount of things. No. So infinity is something that is very hard for our brains to think about because it is something that has no end. So then you get into the paradox of the hotel, right? Imagine a hotel where you have an infinite amount of rooms and an infinite amount of guests, and someone comes in and asks if there's any room for them, and you know every room is already full. How do you accommodate the new person? Well, if it's an infinitely large hotel and there's an infinite amount of rooms, you just ask every person to shift up by one. So the person in room 1 goes to room 2, the person in room 2 goes to room 3, and so on. And you put the new person in room 1. And you can keep doing this, even though the hotel is full. You have an infinite amount of people. You can always do infinity plus 1. So because it goes on forever, you can only fill it with an infinite amount of things. But you can always find a bigger infinity because you can always add more to it. So because infinity has no end, you can always keep adding to it. I can't remember what it's called, but if you look up for like hotel paradox infinity, there's a whole brain teaser that people do around it, like how do you fill up this hotel? You keep shifting people up one room. It's very cool. So yes, infinity does go on forever. No, we can't fill it. More comments here. We were talking about black holes. We were talking about things like that. Pink Floyd concerts. Okay. So there was a comment here by Space Miners that I actually do want to address, where you say there's no such thing as waves, it's all bubbles. The wave is just a cross-section of the bubble. That very much depends on the type of wave. Now, when we're talking about gravitational waves, what you're saying is correct, because gravitational waves propagate spherically. However, waves on water don't. They propagate on a surface. So then it's not bubbles, then it is actually a wavefront. So some bubbles are circular, some waves do have a circular component, and some are linear. And the ones that are linear, like the electromagnetic waves that have electricity going one way, magnetism going another way, those are not necessarily bubble waves, those are planar waves. So it is important to make the distinction there, but I realize you were talking in the context of gravitational waves, and then I agree with what you're saying. Okay, more comments. There was a comment here from Space Miners. Let's talk about dark matter, a substance so strange it's completely invisible to us, yet it's affected by gravity. Yes, cool, isn't it? There is more dark matter than regular matter. Are we insignificant? Love that question. So there is indeed much more dark matter than normal matter. In fact, going back to my trusted pie chart here, everything we see in the universe, everything we know of in the universe, everything from me to the stars, everything that you've ever seen is only normal matter. And normal matter is only 5% of the universe. There's 70% in the form of dark energy, there's 26% in the form of dark matter. We are the most insignificant contribution to the universe. And yet, we are here. We are part of the universe. We are the part of the universe trying to understand itself. Maybe there are dark matter creatures made entirely of dark matter, that are also trying to understand themselves and understand what things are made of and how things work. It could be, but so I get where you're coming from with the question of, are we insignificant? I would say no, because what we do doesn't matter on cosmic scales. Even if we don't correct course and we destroy the environment and humanity is extinct in 100 years, even if we do that, that's not going to matter on cosmic scales. We always say, like, we're destroying the planet. No, we're destroying the planet's habitability. We are not destroying the planet itself. We are destroying the planet's ability to sustain life, being us and every other life form on the planet. But even then, whatever we do there, it is meaningless on cosmic scales. However, we are also here. We are here. We are a blip in the universe's history, barely worth recognizing, barely worth noting in the cosmic. When someone tells the history of the universe, humanity will not be mentioned. But I feel that is also very freeing. It's a very nice thing to think that what we do has consequences for us. We are animated specks of carbon trying to make sense of the scary, confusing universe. And even though what we do is meaningless on cosmic scales, it is meaningful to us. It is relevant to us here now. We are bearing witness to humanity. And that is pretty cool. So this gets very philosophical, but are we meaningless? I don't think so. I really don't think we are. And I know that sometimes talking about these things can give that impression because, the universe is 13.7 billion years old. Humanity has existed for a tiny fraction of this. The universe is mostly dark matter and dark energy. What are we doing here? But I actually find it very freeing to think that what we do doesn't matter on cosmic scales, but it does matter to us. It matters to the people here now and the present. And yeah, I think that's very, very cool. Okay. More comments. There was a comment that I accidentally skipped just now. Where was the comment that I skipped? Yes. From Shawnee. Can vibrations escape black holes? Is it possible for us to send any form of information in black holes? No. Not to our knowledge. Now, in order to escape a black hole, you need to be traveling faster than light in a vacuum. As far as we know, nothing in the universe can travel faster than light in a vacuum, not even gravitational waves. Based on all of our observations so far, gravitational waves also travel at the speed of light, which means they also cannot escape a black hole. So nothing can actually escape from inside a black hole. Now, is it possible for us to send any form of information in black holes? We can send it in. It's never coming out again. Like, everything in the universe is technically a type of information or a type of energy. You can throw whatever you want into a black hole. Please don't throw people into black holes, but they're never coming out again. So no, nothing can escape the gravitational pull of a black hole. because you'd have to travel faster than light in a vacuum, and to our knowledge, nothing in the universe can do that. So no escaping black holes. Okay. Question from Prath. How can Kugel blitzes exist even hypothetically if gravity is so much weaker than the electromagnetic force? Gonna need a reminder as to what a Kugel blitz is here, because I have an idea, but let me just check. What is a Kugel blitz? Right, it's yes. I read that it's an object protected by astrophysics. No, it's an object predicted by astrophysics. Yeah, so the idea of a Kugelblitz is where you have such a strong energy pulse or light that it can actually collapse into a black hole by itself. Fun stuff, especially because photons don't have mass. But it is something where you basically have so much energy. So something we know through is that energy and mass are related. You can convert mass into energy and vice versa. So even though photons have none of what we call rest mass, they do have energy due to their motion. And if you put enough energy contained in the space, hypothetically, this can create curvature of space-time. So we often talk about objects with mass-bent space-time, but you could also say objects with energy, because mass and energy are related. But yes, I feel like I'm going to make a note of Kugelblitz because it's not something I can confidently explain right now, but it's a very cool idea. But yes, let me get back to you on the topic of Kugelblitz. Ask me again next week, Russ. I will have completely forgotten to have checked it out by then. But feel free to ask me about Kugelblitz or Kugelblitzes next week. I feel like what should be the plural of Kugelblitz? I'm Kugelblitz. Zwei Kugelblitzen. So I would say Kugelblitzen, but Kugelblitzes sounds good. Kugelblitz. I will make a note of Kugelblitz and try to. Oh, I realized that I just Googled it, and you'd literally put the definition of Kugelblitz as your next comment. If you try to get enough photons together, they would repel electromagnetically far more than attract gravitationally. Yes. I'm going to have to check Kugelblitz because I cannot explain it off the top of my head, but it is a very weird and funky theoretical concept in astrophysics. So ask me about Kugelblitz next week. Hopefully I will have remembered to check it out. Probably won't, but please do ask me next week. Going back to my idea about the Infinite Hotel, Paul and Prath mentioned different animations and people doing this. Paul says a friend of yours did a great TED animation for this, and Prath says Vera Sataran did a video about the Infinite Hotel. Yeah, there are a lot of videos out there about this whole Infinite Hotel, because it's a very cool mathematical idea of trying to explain infinity. So there is a lot of stuff out there in terms of trying to talk about. I should not do that. Trying to talk about the Infinite Hotel. So if you're curious about infinities, do look into that. It is very cool. I'm doing quick fire questions now because we are at the 1 hour mark, and I probably won't stay on too much longer today. As I've already mentioned, I do have a bit of an injury, and the more I move, the worse it gets. I have been told not to move, which I'm terrible at doing. How many dimensions do we know of, and how many do scientists find these, and how do scientists find these hidden dimensions? For sure, our universe has 4 dimensions: up, down, left, right, in, out, 3 space dimensions, plus 1 time dimension. You have 4 dimensions. Anything beyond that is in the realm of hypotheses and models. We have not been able to find any other dimensions. There are many models of string theory where we try to explain how gravity works on the quantum level that invoke more dimensions. Some invoke 11, some invoke 25, some invoke 5, some invoke 6. Very much depends on your model. For sure, we know there are 4 dimensions. Anything else is in the realm of hypothetical. If at some point we find a convincing model of string theory that makes predictions that we can test, then we can talk about finding other dimensions. You can also, some people look for dark matter composed of extra dimensions with an idea that you have a dimension kind of rolled up and just doing a gravitational thing. This is something that you can look for in different things, like in the CMB, you can look for the way the photons move. Nobody's found any evidence of any further dimensions yet. So we have our 4 dimensions, 3 space, 1 time. That's all we know for sure for now. Anything beyond that is very much in the realm of hypotheticals or theories. Theories, models, not those just theories. Of course, theories are great. Misspoke there. In the realm of hypothesis, models, descriptions that we have that don't quite describe the universe that we live in yet. So for sure there are 4 dimensions. Anything more than that, we don't yet know. Okay, going back to the rubber sheet comment from John, who asked the initial question about rubber sheet. I always thought the rubber sheet was representing 2-dimensional space plus 1D time as a stand-in for 3-dimensional space plus 1D time. I think you can think of it as a slice of space-time in terms of the 2 dimensions. I think it's quite hard to add the time dimension into the rubber sheet analogy. Okay, comment from Paul, which I really like here. This was in relation to the comment of, are we insignificant given that there is much more matter, or there is much more dark matter than normal matter? And Paul makes a comment, if as many think life or intelligent life is maybe far less than 1 per galaxy on average, then we're pretty significant, yes. Of course, even if you say it's like 1 per galaxy, there are billions of galaxies out there. Just like more galaxies than we could possibly imagine, hundreds of billions of galaxies. So then, even if we say there's one intelligent civilization per galaxy, it's still quite a few billion, which means we're not that rare. But yes, life is less common than it could be because there's a lot of things in the universe that could kill us in random ways. And so there's not many places in the universe where one of these catastrophic events hasn't happened in sufficient period for an advanced civilization to develop. So yeah, I think whatever you want, whatever argument you want to use, I think we are significant, and that's pretty cool. Okay. More comments here. Comment from Shortly. What is the purpose of our existence? Oh, we're getting so philosophical. Why did the universe create life and humanity? These are the questions I ask myself. Me too. I think these are very interesting questions to think about. I think these are questions that I can't give you answers to. I can't tell you the meaning of life. I really can't. I wish I could. And I feel like that's not a question that physics can answer, because we move much more into the realm of the why of things. Why do things exist? Why don't they? And I feel like there's no answer that another person can give you to that question. So what is the purpose of your existence? Whatever you want to make of it. In my humble opinion here, I know this is it's a lot of hubris to even try to answer these questions. So what is the purpose of existence? Why is there something instead of nothing? I don't know. And I generally think that that is something that you won't find an answer to in science. It's something that you might find an answer to. Some people find answers in random places. You might look at a tree and tell you, like, this tree is the meaning of life. That's okay. Whatever gets you out of bed in the morning. Maybe your meaning of life today is coffee and chocolate, and that's okay. Whatever works for you. And they're great questions to ask yourself, but the questions that I am not going to attempt to answer for you. Just find some meaning to the existence if you want, or don't. But whatever keeps you happy. Okay. Yes, Prath added the comment when I was trying to figure out the plural of Kugelblitz. Prath said it's Kugelblitzen because it's German. See, that's the conclusion I had reached as well. Kugelblitzen sounds very German. Das Kugelblitzen. Die Kugelblitzen, if I'm making it plural. I've been out of Germany too long. Okay. There's a question from John that I was really hoping somebody would ask me here. I'm still playing catch up with the questions, but there's a question from John. Did you see the paper that said JWST shows the Hubble tension isn't a tension anymore? What do you think of this? Yes, I love this. I gave a presentation on it 2 or 3 days ago when I presented this paper in our journal club. Journal club is where the group gathers and someone presents a new paper that they found and we all discuss it. It is so exciting, in fact, that I'm planning a whole stream about the topic. So thank you, John, for asking me that question. Briefly, one of the biggest questions physicists have been asking themselves over the last 5 to 10 years is, why do we get different answers when we ask the universe, how quickly are you accelerating, or how quickly are you expanding? We get different answers depending on how we ask this question. This is not good. These answers have been spreading further and further apart. One gives us a number of 67, one gives us a number of 73. They're close, but they're not close enough. This is what is known as the Hubble tension. This has been a point of interest for the last 5-10 years for a lot of people. I've written several papers on solving the Hubble tension, but there's a new paper out that says that maybe Maybe there's actually no tension. And that is super exciting and super interesting, and the topic of a stream very, very soon. Yes. And I see we have Sophia in the house. Hello, Sophia. Great to see you. Sophia just finished a bachelor thesis on the Hubble tension. Very nice bachelor thesis, I might add. And yeah, this is a topic we love and care about. So there will very much be a stream about the Hubble tension. And on that note, let me just make some announcements. There are 2 or 3 topics that I'm planning very soon. At some point soon, there's going to be a stream on what's new with the Hubble tension. What's just happened? It's very cool. Another topic I'm going to do soon, I put out a paper back in June. It's a very cool paper. We spent a lot of time working on it, a lot of effort. It's a paper about trying to find gravitational wave, or trying to find early universe physics with our Future's gravitational wave detector. When it came out, I was really busy and didn't really have time to like announce it and advertise it. But now that things have calmed down in a lot of areas, I do actually want to do a stream entirely about the paper that we put a lot of work into. I still need to confirm if I'm doing that stream alone or if one of my collaborators is joining me. I will do a stream about that soon regardless. So within the next couple of weeks, there will be the stream about the Hubble tension, and there will be this stream about my paper. So we're going to have those 2. I see there's a few, I mentioned this paper and there's a few questions. Before I get to there, I just saw there was the tongue-in-cheek question from Prath of, are we sure there's only one dimension of time? Stop trying to break our physics, Prath. This is an ongoing debate where Prath asked what happens if we had 2 dimensions of time. And every physicist I've asked has been like, leave me alone. It's a very cool question, very, very cool question. And that's one that we are still asking ourselves. Okay. Let's see. So there were comments because I just mentioned this Hubble tension paper. Paul is asking, is this another vote like method X now has more evidence, or more like JWST is more authoritative than the other methods? And Pratt has asked, well, can you give a too long read of how they got these answers? Okay, short version. One of the ways we try to measure the expansion rate of the universe is using supernova. Supernova are stars that reach the end of their life and explode. And we can kind of use them as light bulbs. We know how much light they emit. So if we measure the amount of light, we can figure out how far away they are. However, you need something to calibrate. You need an anchor point for your supernova measurements. Up until now, people have always used Cepheids. Cepheid is a type of star that shines, they're kind of like lighthouses. They shine with a specific period and a specific frequency. So we can use Cepheids to anchor our supernova measurements. And we do this kind of multi-step process using Cepheids and supernova to be able to figure out how quickly the universe is expanding. Up until now, all of the data used for the Cepheids comes from data with the Hubble Space Telescope. A team that has existed for years is now using new data from JWST, the telescope that launched a couple of years ago, and they're using 3 different methods instead of just Cepheids to do this calibration. They use 3 different methods using different stars, and when they use these 3 different methods, including Cepheids, they get a value of the Hubble constant that is not too far away from the value we get with other measurements. And so their claim is that basically from what they've been able to see, Cepheids and supernova, or the supernova anchored with something, actually agrees with the CMB value. This would mean their conclusion is we don't yet need a new answer to explain this. It's very interesting. There are some points of criticism in their analysis, and there are some very valid points that they make. So it is very much an interesting paper. It's got the community really excited. I can tell you it generated such a buzz that a couple of days ago, there was actually what is known as a rapid response workshop, where a bunch of experts on this topic, including the people behind this paper and the previous group doing supernova with Cepheids, all of these people came together in an afternoon workshop where there were 3 talks and then a panel discussion. There were like 300 people there. And this is something that was just put together within a few weeks. And it's like, we need the community to respond to this paper now. So it's a rapid response workshop. It was super exciting. I listened to the whole thing. And yeah, I listened to the whole thing, and it was very, very cool. And it's really, this paper has generated a huge buzz. So I really don't want to go into too much detail now. I'm just giving you some general ideas, but there will be a stream entirely about this paper, implications, and what what the different teams or different people involved are saying. Like, what does this mean? Why should we believe this? And comment from Paul. Now I know why Deanna's excited. Maybe the CMB was right all along. Yeah, who knew? Who knew? But also, like, if the Hubble tension suddenly disappeared, if we figured out that it was solved, it would be very, very interesting because it means we've understood something more about the universe. But it's also, a lot of us, myself included, have spent a lot of time trying to figure out cool and creative solutions. Like, what if dark matter is up to weird stuff? What if dark energy is up to weird stuff? What if gravity is up to weird stuff? And if it turns out that the answer is the stars are up to weird stuff, some people will be disappointed by that answer. But it's very interesting. It's very exciting. So there will be a stream soon about this. I don't want to pin an exact date just yet, but it might even be next week. I will announce it in advance, as always. Yeah, I think within the next 2 or 3 weeks, maybe next weekend. Okay, unless I say otherwise, next weekend we'll do the Hubble tension stream because it's such a cool topic. So potentially Sunday 22nd we do this. I will let you know if there's a change of schedule, but potentially next Sunday we'll do the Hubble tension stream because I've already read the paper, I've already attended the conference. It would be an easy one to do. The only reason I didn't do it today is because I didn't really have energy. So, okay, next week we go in detail about why JWST has killed the Hubble tension, what this means, and where we go from here. So that's going to be exciting. So thank you for asking me about that, John. I was very much hoping somebody would ask me about that because it is a very cool question, and it does let me advertise next week's stream. So next Sunday, same time as always, that is 8 p.m. if you're in Finland, like I am, 7 p.m. if you're in mainland Europe, 1 p.m. if you're on the west coast of the east coast of the US, 10 a.m. if you're on the west coast of the US. As always, there is a time zone converter on cupofcosmology.com where you can figure out when the next stream is happening in your own time zone. But next Sunday, Hubble tension. And then potentially the week after or the following week, I'll talk about the paper we put out recently because that's pretty cool. So there are plans, there's stuff happening, and there is still stuff happening behind the scenes. I've mentioned before that there is going to be kind of an expansion to Cup of Cosmology, the extended edition, the extended universe. That is also still happening. I know I haven't talked about it. I did put all of those plans on pause the last couple of months, but there is still stuff happening behind the scenes. So there is more stuff happening with Cup of Cosmology. I just want to make a comment that now that we're in September, it means Cup of Cosmology has entered its 10th year. My first stream with a different name, like it wasn't called Cup of Cosmology at the time, my first live stream of I'm a cosmologist, let's chat about the universe, was in August 2015. So we are just entering the 10th year of Cup of Cosmology, which is mind-blowing to me and amazing. So let me just take this chance again to thank everybody. Those of you who comment, who watch without commenting, who lurk, if you send me emails, if you send me questions, if you've interacted with Cup of Cosmology in any way, thank you. Really, thank you. I started this project years ago as just like, let's see what happens. And I did not expect it to become such a long endeavor. But I'm really glad. I've learned a lot. I hope you all have as well. It's been a really fun journey. And I'm really looking forward for the next parts of Cup of Cosmology and the future of Cup of Cosmology. Not planning on going anywhere anytime soon. So it's exciting. I'm glad you're all here, and I'm glad Cup of Cosmology is still here. And then I get to tell people about the cool stuff I work on, which is always so much fun. Okay, I'm pretty sure I got through all of the questions today. I know there's a lot of comments that I wasn't reading because I'm not sure if they were questions or just comments, but I think I got to all of the questions, hopefully. If not, feel free to reach out. You can always email me, contact@cupofcosmology.com. I might not reply quickly, but I will reply eventually. And you can also follow me on Instagram and Cup of Cosmology. Basically, Cup of Cosmology on all the socials, except for TikTok for now. So, Cup of Cosmology on all the socials. Feel free to reach out if you want to. Okay, thank you everyone for joining over the last 9 years. Thank you for joining today. There have been a lot of cool questions, a lot of cool comments. I always love coming on and just seeing what random direction you're going to take the chat in. And it's been really fun, as always. So, Cup of Cosmology should be online next week. Same time as always, with a special focus on the Hubble tension and what JWST is telling us about the Hubble tension. I hope to see you all again next week, same time as always. And I hope in the meantime, you all take care of each other and stay curious.